turn the remote on? There we go. So, anybody recognize the name William Earl Talbot II? Anybody ever heard of him? Wow, I guess he's not as famous as I thought. I can tell you one thing about him. I hit the right button. He hates genetic genealogy. And genetic genealogy is a way of matching samples for DNA. So I'm going to let you find out with a short video as to why he really, really, really hates genetic genealogy.
So far this year, law enforcement has identified over 70 suspects using a new technique called genetic genealogy. This is the same tool that detectives in California used last year to identify the so-called Golden State Killer. In the first of two stories, William Brangham explains how this tool works and why it has raised serious privacy concerns. It begins with the murder of a young couple in Washington State, a case that became the first ever genetic genealogy case to go to trial. This is part of our Leading Edge series on science and technology.
In 1987, under the High Bridge in rural Washington State, a young man named Cooke was found murdered. His girlfriend, Tanya van Kylenburg, was found in the woods 60 miles away. She'd been raped and murdered. The only piece of evidence was semen from an unknown man found on Tanya's clothes. But it didn't match anyone, even after police DNA databases developed in the following years. Eventually, the case went cold. But 18 years later, Snohomish County Detective James Scharf picked up the case. He turned to the public for new leads.
There's a green backpack that the person might have had, a black jacket, and a Minolta camera.
But still, nothing.
These were totally innocent kids, 20 and 18 years old. So this was a case that I really wanted to solve.
But the person who would eventually help crack the case was not in law enforcement at all. C.C. Moore is what's known as a genetic genealogist, someone who helps people trace their family ancestry.
By about 2012, I think it was starting to kind of bubble to the surface with a few of us that what we're doing could have law enforcement applications. But it wasn't time yet. The databases were too small.
But that was all about to change when commercial DNA testing suddenly went mainstream.
Don't just give a gift. Give them Ancestry DNA.
DNA testing services like Ancestry.com and 23andMe have exploded in popularity. It's estimated that more than 26 million people have now used companies like this. The process of testing your DNA is actually pretty simple. You order the kit online. These each cost about $100 each. And then you just spit some saliva into a tube like this, you mail it in, and in a few weeks, you get your DNA reports. As millions of people started getting their DNA results, many of them copied their data into other public websites so they could better find distant family members. But C.C. Moore realized this wealth of information could also be used to help solve cold cases.
We have two matches at the top of the list that are both sharing about 3% of their DNA with the unknown suspect.
She demonstrated how she did it in the Cooke van Kylenburg case. She took the unknown suspect's DNA from that semen sample and compared it to DNA results in the databases. She found two partial matches, people who were likely the killer's two second cousins.
So if you share 3% of your DNA with someone, then you're most likely second cousins, which means you share great-grandparents. So I'm going to build these trees back to great-grandparents.
From there, she went back in time, up the family tree, up to the great-grandparents of those cousins.
We should find the common ancestor at this level somewhere with the unknown suspect.
From there, moving down the family tree, she searched public documents and obituaries to find where these two families converged. This family would likely be the suspect's immediate family, his parents and siblings.
But from the DNA, we know it's a male, and these are daughters.
This was how she identified the likely culprit.
This allows me to zero in on just this one male as the potential suspect. It was a very odd moment to be looking at the name of the person I believed to be a killer and know that I was the only person in the world who probably knew what he had done other than himself. But this was a very heavy discovery, and I just wanted to quickly get that name to Detective Scharf and get that off my shoulders.
For Detective Scharf, this was a huge lead, but not enough to make an arrest. He'd need actual DNA from the suspect to know for sure. And so, a coffee cup discarded by the suspect was collected by the police and tested. When the results came back, it was a match.
And I got tears in my eyes, and then I screamed that, yeah, we finally got this case solved. It was just such a wonderful feeling.
Yesterday, we took into custody a 55-year-old SeaTac man who is suspected of the 1987 murders of Cooke and Tanya van Kylenburg.
This summer, 56-year-old William Earl Talbot II went on trial for the murder of Cooke and Tanya van Kylenburg. Talbot pled not guilty and never took the stand. His lawyers argued that the presence of Talbot's semen at the crime scene could have been from consensual sex.
There was evidence consistent with sexual intercourse, but not injuries associated with assault. She wasn't bruised and battered. There wasn't evidence of sexual assault.
The only definitive thing linking Talbot to the crime was this DNA match. After 2 days of deliberation, the jury convicted Talbot of first-degree murder for both Cooke and von Kylenburg. He was sentenced to life in prison. This was the first ever trial and conviction on a case cracked open by genetic genealogy.
Without genetic genealogy, this case never would have been solved. C.C. Moore did in 2 hours what 20 or 30 cops couldn't do in 30 years of working on this case. That's how powerful genetic genealogy is in solving crimes.
In our next story, we'll explore the deeper privacy implications of this technique and why some are so concerned about this new crime-fighting tool. For the PBS NewsHour, I'm William Brangham.
Was solved by looking at the DNA. Very, very important technique that has been developed. By the way, on last Wednesday night, there was a new Nova, and it was about this case and some more, such as the California one, in great detail. It was really well done, and a lot more on the technology that was involved, explaining exactly how it works. So I highly recommend looking at that if you care about this. So, gel electrophoresis, that's how it's done. Last week, we went over how to make the buffer, a tris buffer, and a gel, and we prepared those for electrophoresis. The next step is to carefully remove the comb from the gel, leaving wells for each sample. Unfortunately, when I removed the comb from the well, it tore the gel apart. And if the wells are destroyed, you start the whole thing over again. But I decided that the combs that we had are not slick enough. So I put a very thin coating of Vaseline on them. And then I was able to, today, remove the combs from the gels with no effort at all. It worked perfectly. The next step is loading the samples. The samples of DNA that you have are first digested with particular restriction enzymes in order to break them up into pieces. Then a loading buffer is added to each sample. Loading buffer has sustain in it so that you can see the sample as it's moving, and it also makes it more viscous or denser, so that when you pipette the sample into the wells in the gel, that it will stay where you put it. It's very important that it not float away. The samples have to be pipetted very, very carefully. You have to make sure they're going into the right well. You have to be careful you don't puncture the well. In the first drawing, it's being, the first photo, it's being done perfectly. And you can see that because it's more dense, it is sinking to the bottom of the well. In the second one, the person has punctured through the well. And that means the sample is going to go out and be underneath the gel and get diluted, and it will not be of any use at all. When pipetting, it's important to use your secondary arm. You pipette with your primary arm and use the second one to hold your arm to try to keep it steady and get it just right. Then a current gets applied to the gel because DNA, recall, is negatively charged. So the samples are going to migrate through the gel towards the positive end of the electricity. The biggest fragments are going to migrate the least distance, and the smallest ones will move the most. The big ones too heavy and take up more space, more difficult to move through the gel. To see the riflips, remember that's restriction, fragment, length, polymorphisms, the segments that we get from digesting with the restriction endonuclease. We need to add a stain to the gel. And then we wash the gel. We cover the gel with stain. This is after it's finished running. Cover it with stain. And then we have to wash the stain away, the excess stain, so that we can see. Otherwise, you just got a big piece of blue gel. Ethidium bromide is commonly used as a stain. However, it's very toxic and a potential carcinogen. So instead, we use something called Carolina Blue, called because it's made by Carolina Biological Supplier. It's a much safer thing to use. It's very safe. The only danger is that it is a dye. So it will stain skin, it will stain clothing. You have to be sure you're well protected. Then you wash with water. You simply put it in a dish with water, let it sit for a long time, take it out, change the water, put fresh water in, each time distilled water, and you wash the gel usually 3 times to get it to where you can see properly. So you end up with a gel, it might look like this. And you can compare, now the vertical columns are each a lane for one sample. The sample is put in, and then because of the electrical charge, that moves along. And the smallest fragments move the furthest. And what we usually do in the outer lane is put a control, something that we know the size of it. And when we do size of DNA fragments, we do it in base pairs, the numbers of base pairs. This is another gel, same thing, just a little more complex, with a lot more samples being run. So I'm going to give you a scenario. OMG, is that blood? Laurel nearly broke Marcus's arm as she tried to push past him into the classroom. Marcus grabbed the sleeve of her cardigan and yanked her back. Don't! Can't you see the glass? Laurel tried knocking his hand free, but the 6'4" varsity basketball captain held tight. He made her settle for looking from under his armpit. Not that what she saw would make any sense. Their classroom lab looked like a riot scene. 4 chairs and a potted plant were overturned in the center of the room, and broken pieces of glass were scattered across the floor, along with several wet red drops. Plink, plink, plink. Marcus's eyes were drawn to the teacher's desk, where droplets of brownish liquid fell from a paper cup and collected in a puddle on the linoleum. "What happened?" Laurel asked. "Did somebody get hurt?" Laurel and her classmates had gathered in front of the door and strained to see inside the room. Marcus inspected the scene and raised his right arm above his head, his fingers spread apart as if taking a shot from the free throw line. "Stay back!" "Where is Miss Mason?" Lauren said. "She told me she would meet me here before class to review for the quiz." "Okay, folks, keep it down." Mr. Gladson, the teacher in the classroom next door, came into the hall. His white lab coat was streaked with several rust-colored stains. The pungent odor of formaldehyde permeated the corridor. "In case you haven't noticed, the bell has rung." He wiped his nose with a tissue and then tossed it into a nearby trash can. A girl's fake shriek from inside the anatomy lab rose above the buzz of Marcus's classmates. "What's going on?" Bobby's high-pitched whine was unmistakable, and so was the scent of his bubble gum. "I think something might have happened to Miss Mason," Marcus said. He dug around in his backpack and pulled out a magnifying glass. "We've got a crime scene to process." "Go figure," Laurel said, Sherlock Holmes in a varsity jacket. For the next hour, Marcus and Laurel searched the classroom and discovered several pieces of evidence that Marcus described in his notebook. Later, you can review these by watching the video again if you need to. 10 small drops on the floor, confirmed by Kastle-Meyer test to be blood. That's a technique used to find out whether something is blood or not. A shard of glass from a broken 500 milliliter Erlenmeyer flask, the edge smeared with a reddish stain. A paper cup with lipstick stains, presumed to be Miss Mason, found on her desk. A wad of bubble gum stuck underneath an overturned chair. Mr. Gladson's discarded tissue recovered from the trash can in the hall outside the lab. A copy of email from Mr. Gladson to Miss Mason, asking her to give up her position as department chair. Bobby's test on photosynthesis with a large F scrawled in red ink on the first page. Marcus knew the game was afoot. So we have a mystery. What happened? Well, we're going to do a gel electrophoresis of samples that we get from the scene. Samples of the blood and that were recovered from other places. The results of the gel electrophoresis then are going to be measurements of how far each rift lip moved from the well. They each get carefully measured. The measurements for the distances in the control, that one lane that has a control of known sizes of rift lips, are plotted against the number of base pairs for each fragment using semi-log graph paper. Now it's called semi-log, and this is an example here because the axis, one of them is linear, normal, and the other is logarithmic, such as going 1 to 100, and then 100 to 1,000, and 1,000 to 10,000, and so on. So, I got an example from somebody of one control that was run using this data, giving the number of base pairs involved in the fragment and how far it moved in centimeters. That data is used to form a standard curve that then the other samples can be compared to. And you find out whether or not they match up. Note that each gel has to have its own standard curve because the amount of movement in a gel would vary with the time that it is run with the electricity. And there are other variables that also can affect it, such as the consistency of the aqueous gel. So you always have to have a different standard or a new standard in each gel for comparison. So I plotted a graph, logarithmic graph, with the data points I just had up there. And I sort of cheated a little because I just put the data into Excel and then did some manipulations to turn it into a semi-log graph. And then did a best fit line, but using a logarithmic line. So you end up with that, and then you can take any known you want to, unknown you want to compare it with, and you look at the number of base pairs, go up to the line, and then go over to find out, I'm sorry, I said that backwards. You look at the distance that it moved, go over to the best fit line, and then go down to find out how many base pairs it was. And in that way, you can compare the different samples, even if they're run on different gels. Okay? So our next step was going to be to run the gels tonight. However, we ran into a small problem in that we are missing part of what we need for it. So I'm afraid we're going to have to postpone that lab until we get the materials that we need in order to do it. If anyone has any questions, please ask now.